This system has many mirrors that are located here and focus the solar radiation here, into this mass of stones which are heated by the solar radiation to approximately 1000 degrees Celsius during the summer and keep this temperature for several months in order to use this thermal energy in the non-solar winter, and all that was experimentally tested by this system that started operating 15 years ago.
Let's apply this system for space heating of one house in Sweden, which is known as the country of the Vikings, whose character was trained by terrible northern winters. This is the climate near Stockholm, where we will locate that house. This system produces too much energy, enough to heat a dozen houses, and therefore we reduce it to this diameter, 17 meters, and the stones of this heat storage must be located inside these dimensions. It is interesting that this mirror system can be used as a gazebo, including during the sun, but people should avoid this hot zone, although we see that hot zones can be a decoration of gazebos. Or we can use that hot zone as a barbecue or a stove, and now I am showing systems which should focus solar radiation for cooking. In addition, we can stop this energy flow if we command these mirrors to be in this horizontal position. I was just talking about these upper mirrors, and they have the opportunity to change their inclination like this simultaneously and equally for all mirrors. The purpose of these mirrors is to direct the sun's rays vertically downwards. Now I will repeat the same, and the upper mirrors are located here, and then these vertical rays must be focused by this lower mirror, which consists of reflective hoops, similar to that mirror in Serbia. Therefore, the upper mirrors change their inclination according to the change in the height of the sun above the horizon, and all the upper mirrors are fixed on a circular platform that rotates according to the movement of the sun across the sky. Unfortunately, these upper mirrors do not perform well during low sun due to these shadows from the more southern mirrors. But increasing the height of the sun also reduces the efficiency due to the decrease in the cosine of the angle of incidence of the sun's rays on the mirrors. That is why I calculated this graph of the upper mirror efficiency, which is maximum here during not very high sun, about 30 degrees above the horizon, which corresponds to spring and autumn in Sweden. My future videos will describe some better options with a graph like this, 2 or 3 times better, and they will not have this expensive lower mirror. It is obvious that not all of this energy will penetrate inside those hot stones, because some of the solar energy will be lost when reflected by the hoops of the lower mirror and when passing through this glass. In addition, the reverse flow of heat and thermal radiation increases rapidly as the temperature of the hot stones increases. The final result will be even worse due to dirt on the glass on the upper mirrors and on the hoops of the lower mirror, and due to solar photons missing this glass and the hoops of the lower mirror. All these factors are taken into account in this graph, which describes how much thermal energy comes to the hot stones from our small system with a diameter of 17 meters in the climate of Stockholm. Our upper mirrors are not round but rectangular, with a total area of 207 square meters. Reducing the number of upper mirrors leads to an improvement in their efficiency when the sun is low above the horizon, because these southernmost mirrors are not covered by those shadows. We can notice that January and November have bad heat production. Moreover, our system does not work at all in December due to the fact that this reverse energy flow exceeds this energy flow from the mirrors, and therefore it would be better not to turn on the system in such cases. This is because Stockholm is located far to the north, where the sun rises very low above the horizon from October to February. At the same time, this graph of the heating needs of that house shows that these 3 winter months require the maximum amount of heat. These graphs are repeated in the columns of this table, and this is the heat production of our mirror system, and this is the heat extraction from the hot stones for the space heating of the house. In addition, these are thermal energy leaks from those hot stones. It is obvious that if this energy inflow is greater than the sum of these two columns, 68 tons of the hot stones are heated in this way from 100 degrees Celsius in March to 800 degrees in July. But over the next 7 months, the temperature of the hot stones decreases from 800 degrees to 100 degrees in this way. It is not difficult to verify that this extraction of thermal energy completely 100% covers the heating needs of a house with an area of about 100 square meters in the climate of Stockholm. You may have noticed that only a third of this heat production is used for the space heating of the house, and the remaining 68% is lost as heat leaks from our heat storage. Of course, this soil is a thermal insulation, but the main resistance to the heat leaks is performed by this thermal insulation with a thickness of 2 meters. These outer layers can be cheap mineral wool or urea formaldehyde foam, but these inner layers are made of more expensive thermal insulation for temperatures up to 800 degrees Celsius. The support for the heat storage is this aerated concrete, and these empty spaces are filled with urea formaldehyde foam or other thermal insulation. Before compiling that table, I calculated this graph of the power of those heat leaks through the thermal insulation of the heat storage and the soil on the basis of this deterioration in thermal conductivity with increasing temperature. But we remember that our heat storage has this hole, and accounting for energy loss through its glass could increase these total heat losses by approximately 4 or 5 times. That is why here we also install 6 thermal insulation, which opens automatically only during the sun, but closes automatically when the sun disappears, and therefore the total heat losses increase not several times, but only by a few %. Unfortunately, the Swiss did not describe the system of absorption of this radiation inside the heat storage and the system of transferring thermal energy from the hot stones to the home heating system, but my future videos will describe various solutions to these problems. Also, the Swiss did not describe the inside of their heat storage, and therefore my calculations assumed high thermal conductivity of the hot stones, while reducing the thermal conductivity can significantly reduce those heat leaks.